So our kinetic molecular theory is a theory in itself, okay? It's based on the idea that all particles of matter are in constant motion. So every single particle, every atom, every molecule is always in constant motion. If we would reach a point where molecules would stop moving, does anyone know what that's called? Where it comes to an absolute stop, what's it called?
Absolute zero.
Yeah, it's called absolute zero. And what temperature is that?
0 Kelvin.
Yeah, 0 Kelvin, or negative 273 degrees Celsius. It's this point where we theoretically think everything would come to a stop. Have we ever reached that point? No. Okay, scientists have gotten very, very, very close, yes, but we haven't reached that absolute point where everything stops. Okay? But theoretically, we think it's at 0 Kelvin. Okay? So this kinetic molecular theory and these gas laws that we talk about have this basis that everything is in constant motion. Okay, so we're going to look at the theory's connection to gases, liquids, and solids. We're going to kind of go over the states of matter again to make sure we review what the properties of solids are, liquids are, and gases are. So we're going to review that just a little bit, but we're going to look at this kinetic molecular theory in connection with all of those states of matter. So when we're looking at this kinetic molecular theory and we're dealing with these ideal gas laws, we want to consider something that we call an ideal gas. Okay, something that works in this perfect world that might not be totally real life, but we're going to work with something called ideal gas because it gives us a perfect scenario of what we think is going on. Okay, so this ideal gas that we're going to work with is this hypothetical, and it fits all of these assumptions of the kinetic molecular theory. And there's 5 assumptions that we're going to go through. Okay, so it has to fit these 5 assumptions in order for it to be an ideal gas. All right, so let's talk through these assumptions, okay? There's 5 different assumptions that something has to meet. They're kind of like criteria, okay? 5 different kind of criteria that it has to meet in order for it to be an ideal gas. Okay, so this first assumption says gases consist of a large number of tiny particles that are far apart relative to their size. And what that means is in a container, we might have 10 particles of gas, we might have 10,000 particles of gas molecules, but they're going to still be what we consider far apart. They're going to be bouncing, they're going to be moving, they're never going to stick together, right? Do you ever have a gas that you see just kind of stick together? Does smoke just stick in one place? Do you see those particles stay together in one place? I know smoke isn't technically a gas, but it kind of behaves like that. Those gas particles don't just sit in one place. It moves throughout the air, okay? And when it fills the container that it's in, what's that called? Does anyone know that term? When gas particles kind of move throughout the air to fill their container, that's called they're diffusing, right? Have you ever heard that term before? Okay. They're diffusing throughout the air. So these gas particles, no matter what the size of the container, they're always going to be far apart. They're never going to be sticking together, okay? They might collide, but then as soon as they collide, what would happen? Yeah, they bounce apart. Okay, so that's kind of what we're looking at here with our gas molecules. They're little, and they're bouncing apart. Okay, gas particles are farther away from each other than in a solid or a liquid, and most of the volume of a gas container is considered to be filled by blank space. Okay, so even in a container that contains only air, most of that is still blank space. There's air particles, oxygen particles, nitrogen particles floating around, but most of that is just a blank space. So that's our first assumption, is that they have tiny particles that are far apart. Okay, gas particles don't stick together. Okay, so these types of collisions between gas particles and the particles and the wall are what we consider elastic collisions. And in physics, we'll learn about elastic collisions. Okay, we just happened to get through that in both of our physics classes. Elastic collisions are collisions where things collide and then bounce apart. So just like we described earlier, we've got collisions between particles in which they collide and they bounce apart. Okay, so an inelastic collision, or the opposite of that, would mean they collide and stick together, and that's not what gas particles do. But when we say there's no loss in kinetic energy, that means every single ounce of energy basically in that particle is being transferred to the other when those two are colliding. Okay? So they will bounce and go apart with each other's kinetic. Our third assumption is that we have gas particles moving in continuous random motion. Okay, and rapid. So do gas particles move slowly, you think? No. Okay, they have to move quickly. What makes gas particles move faster? What would you think that might make gas particles vibrate or move faster? Yeah, heat. Adding heat to a gas makes it move faster. Okay? It raises its kinetic energy. That causes these gas particles to all move in continuous. Assume that there's no forces of attraction between gas particles. Okay? We're going to assume that these gas particles are constantly repelling each other. They're not going to attract each other. They're going to repel. All right, and our last assumption tells us the temperature of a gas depends on the average kinetic energy of the particles. Okay, temperature of the gas depends on kinetic energy. So that means if we raise the temperature, what happens to the kinetic energy of these particles? Yeah, they gain kinetic energy, and it kind of works vice versa. So if they somehow gain kinetic energy, that's going to force the temperature to go up. So even though we think that raising the temperature causes an increase in energy, it kind of works backwards. So as they start to increase energy, that's going to cause an increase in temperature. Okay, so we kind of think that we control the temperature when it's really not. Like they control the temperature, right? The little particles and their kinetic energy control the temperature. What are ways that we add kinetic energy to a molecule? We talked about it just a second ago. What are ways to add or make them move faster?
Heat.
Yeah, heat. So heat is the way that we control this kinetic energy, which then raises the temperature. Okay? Questions so far on our 5 assumptions? Okay. So now let's kind of look at what it means to be a real gas. All right, so particles in real gases, they do have their own volume. Okay, so that means each little tiny particle of gas does take up some amount of space. In ideal gases, we don't really consider that volume because it's so small. Okay, but in real life, particles do have a volume. In real life, they do have a tiny attraction to each other. Okay, the electrons within those gas molecules are kind of attracted to the nucleus of those other gas particles. Okay, so in real life, they do have very tiny volume, and they do have very tiny attractions between them. For our kind of ease, we ignore those small values. Okay, gas behavior in real life is mostly ideal, except when we have very low pressures, very high temperatures, and when we have non-polar molecules. Okay, can anyone tell me what a non-polar molecule is?
H2O.
Okay, H2O is nonpolar, yes, but do we know why it's nonpolar? What makes an atom nonpolar? Opposite. Nonpolar means that they're shared evenly. So a nonpolar molecule is exactly symmetric, and all those electrons are shared evenly. So Amanda, what you're describing is a polar molecule. And I know it's a little bit counterintuitive that a nonpolar means it's shared evenly, but I didn't make up the rules. Okay? So for the most part, gases do act like ideal, except when we have these conditions. Okay? Liquids always have a definite volume, but not a definite shape, right? They're one of the states of matter that takes the shape of their container. Okay, so always a definite volume, but not a definite shape. They have particles that are closer together than in gases, but these liquids are kind of always the middleman. Right? They're closer together than gases, but farther apart than solids. Okay? These guys have stronger intermolecular forces than gases do as well. Okay, and intermolecular means that between those particles, if I've got 2 water molecules, those 2 are strongly attracted to each other, much more strong than gases. So inter is between those particles. So even in liquids, we've still got we've still got particles in constant movement. So in liquids, they're not bound to one shape. They're not locked into that grid, that crystal lattice. They're not locked into that. So they still have the ability to move. Do they move as much as gas particles do? No, they don't. Okay? Their movements might be smaller in kind of force. They might be more vibrations than a real rapid movement. Okay? But they are still in motion. I know this is a lot of review, so. In solids, we have really, really closely packed particles, much more closely packed than liquids or gases. Forces. So their intermolecular forces are the absolute strongest. They really, really draw those other molecules to themselves, okay, or vice versa. That we have really strong intermolecular forces. It's harder to break solids and it's harder to break liquids or break gases. I know break is not the right term, but it's harder to disturb those. Okay? Particles are still in constant motion even in solids. So even though everything around you is a solid and it doesn't feel like it's moving, those particles are in very, very small vibration movements. Okay, so those particles are still in constant, rapid motion, but it's just a little bit less noticeable than water or any other liquids or gases. Okay. All right, so let's go ahead and start that now. We should have time to get through most of it if you work fast.